Hey, welcome back. Today, we're going to dive into one of the most, I think, elegant algorithms in all of quantum computing. It's all about how you can crack a secret code, not by trying over and over, but with one single, perfectly aimed quantum question.
So imagine you're playing a game. There's a machine, it has a secret code, and your job is to figure it out. Pretty simple, right? But here's the catch. You want to do it in the fewest possible guesses. Well, what if I told you that with a little bit of quantum magic, you could find the entire code in just one shot?
Okay, so let's set the stage for this game. We have a machine, sort of a black box. We can put questions in, we can get answers out, but we have no idea how it works on the inside. And hidden inside that box is a secret string of bits. Our one and only job is to figure out what that string is.
And that secret code? It's what we call a binary string. It's really just a sequence of zeros and ones. You can think of it like a row of light switches. Some are on, some are off. This string is the secret, we'll call it S, that we are trying to find.
Now, let's think about this for a second. How would you normally solve this? If you're using a regular, everyday computer, what we call a classical computer, the strategy is, well, it's pretty straightforward, but it's definitely a bit of a grind. Really, your only option is to check every single bit, one by one by one. You'd have to ask the machine, okay, what's the first bit? It gives you the answer. All right, now what's the second bit? It tells you that one. You just have to keep doing this over and over again until you've got them all.
And here's the crucial part. If your secret code is, say, n bits long, you have to ask n separate questions. There is just no way around it. An 8-bit string, that's going to take you 8 queries. A 64-bit string? Yep, 64 queries. It is a strict one-to-one relationship.
But this is where quantum computing walks in and just completely flips the table. See, back in 1992, two physicists, Ethan Bernstein and Umesh Vazirani, they came up with an incredible quantum shortcut that just turns this whole problem on its head.
The Bernstein-Vazirani algorithm, as it's called, uses a fundamental quantum idea, superposition. You've probably heard of it. It's what allows a quantum bit, a qubit, to be in a state of both 0 and 1 at the exact same time. So by using this property, the algorithm can ask a single super question that basically queries every single bit in that secret string, all at once.
And this really shows you the night and day difference, right? The classical way is slow and steady, just plodding along one bit at a time. But the quantum method, it's completely parallel. It gets every piece of information it needs in one single go.
So just to recap, the classical method for a string with n bits, that's going to take you n queries.
But with the Bernstein-Vazirani algorithm, just one. A single query reveals the entire n-bit string. And listen, it does not matter if that string is 8 bits long, or 8,000, or 8 million bits long. It is always, always one shot.
And that incredible jump in efficiency, that is a perfect textbook example of what we call quantum speedup, or quantum advantage. It shows a problem where a quantum computer isn't just a little bit faster. It is fundamentally, powerfully better than a classical one.
Now, this code-breaking game is a really cool way to demonstrate the power, for sure. But the algorithm's real-world importance today is actually a little bit different. It's become one of the most vital tools we have for testing and verifying real quantum hardware.
You see, this algorithm is part of a whole family of foundational tests for quantum computers. You've got others like Grover's search and Deutsch-Jozsa. Each one is designed to poke and prod a different aspect of a machine's performance. But what makes Bernstein-Vazirani so special for testing is right there in the table, its delta function output.
So what on earth is a delta function output? Well, to put it simply, it means the algorithm is designed to give you a single 100% certain answer. There's no guesswork. A lot of quantum algorithms spit out probabilities, but this one, it's supposed to give you one clean, unambiguous result, the exact hidden string you were looking for, period.
And that makes it an almost perfect diagnostic tool. The engineers know exactly what the answer should be before they even run it. So if they run the program and get anything else, even something that's just a little bit off, they know immediately that there's noise or some kind of error in their quantum processor. It's the ultimate pass-fail test for their hardware.
So let's just zoom out for a second and wrap this up. Why does this seemingly simple algorithm, something from the early 90s, still matter so much today?
Well, it really comes down to this.
First, it was one of the earliest and clearest examples of quantum superiority, that incredible, undeniable leap from n questions down to just one. And second, because its answer is so predictable, it has become an absolutely essential tool for the engineers who are on the front lines, actually building and debugging the powerful quantum computers of the future.
And you know, that really leaves us with a pretty fascinating thought. This algorithm is all about finding a hidden linear pattern in a single step. It really makes you wonder, what other, much more complex secrets may be hidden in nature, or in financial markets, or even in medicine? What could we unlock if we just knew the right quantum question to ask?